The universe is a vast and intricate tapestry woven with celestial bodies, from the smallest asteroids to the largest galaxies. At the heart of this cosmic ballet are the stars and their orbiting planets, each playing a crucial role in the story of the cosmos. Understanding how these planets come into being is not just about satisfying curiosity, but about unraveling the very processes that led to our own existence. Planetary formation is a journey that begins in the cold, dark corners of space within clouds of gas and dust. These stellar nurseries, though seemingly serene, are the birthplaces of complex processes that lead to the creation of star systems like our own. The story of how planets are born is both a testament to the complexities of the universe and a narrative of creation that mirrors many of the processes seen in nature here on Earth. By delving into the origins of planets, we peel back the layers of cosmic evolution, revealing not just how celestial bodies form, but also how they sustain the cycle of cosmic rebirth and destruction. This journey through space is not just about understanding the universe, but about appreciating the delicate balance that allows for the existence of places like our Earth. In the vastness of space, regions known as stellar nurseries or molecular clouds serve as the cradles for star formation. These clouds are primarily composed of hydrogen gas and dust, accumulating under the influence of gravity. As these clouds contract, they begin to break into smaller, denser fragments, setting the stage for the birth of stars and their planetary systems. As the density within these fragments increases, the core temperature rises, eventually triggering nuclear fusion. This process marks the birth of a new star, radiating energy and influencing further accumulation of material in the surrounding space. It's this energy that eventually leads to the formation of a protoplanetary disk around the new star, the first step towards the birth of planets. The life cycle of these stellar nurseries is a delicate balance between gravity pulling material inward and the energy from new stars pushing it away. This interplay is crucial in determining the number and types of planets that can form around a new star. Without it, the potential for planetary systems like our own would be vastly different, showing how integral these processes are to cosmic architecture. Following the birth of a star, the remaining gas and dust begin to orbit in what is known as a protoplanetary disk. This disk is the factory where planets are constructed, composed of silicates, ice, and other compounds. These materials slowly begin to coalesce under the influence of gravity, forming the building blocks of potential worlds. The protoplanetary disk is not just a passive collection of material, it is a dynamic and turbulent place where particles collide and stick together. This environment is crucial for the gradual growth of these particles into larger bodies. Over time, these collisions result in the formation of planetesimals, the next critical step in planetary formation. This disk is also a scene of intense competition, where growing bodies vie for material to increase their mass. This competitive accretion is fundamental to the process of planetary formation, determining which bodies will grow large enough to become planets and which will remain as smaller asteroids or comets. The dynamics within this disk encapsulate a miniature version of natural selection, observed on a cosmic scale. Planetesimals are the solid chunks of matter, typically ranging from a few kilometers to hundreds of kilometers in diameter, that serve as the basic building blocks of planets. Formed from the dust and debris in the protoplanetary disk, these bodies are the result of countless collisions and accretions of smaller particles. Their formation is a critical step in the planetary formation process, as they represent the initial solid mass that can accumulate to form larger planetary bodies. As planetesimals orbit the young star, they continue to collide and merge, growing gradually over time. This process of accretion can vary widely in duration and intensity, depending on the distance from the star and the density of the disk. These variations significantly influence the composition and size of the resulting planets, showcasing the diversity observed in planetary systems across the universe. The role of planetesimals extends beyond mere building blocks. They also contribute to the clearing of the protoplanetary disk. As they grow, their gravity helps to sweep up smaller particles and debris, clearing paths and potentially influencing the formation of other nearby bodies. This cleaning process is essential for the stability of the emerging planetary system, setting the stage for the next phase of development. Once planetesimals form, the stage is set for the creation of protoplanets, larger bodies that are on their way to becoming full-fledged planets. These protoplanets form as planetesimals collide and fuse, a violent and chaotic process that leads to the gradual accumulation of mass. This stage is crucial as it determines the core composition and initial size of the future planets. During this phase, the protoplanets undergo significant changes. As they grow larger, their gravitational pull becomes stronger, attracting more and more debris from the surrounding disk. This process not only increases their size but also heats up their cores, potentially leading to volcanic activity and the outgassing of gases, which can form primitive atmospheres. This phase is not just about growth but also about differentiation, the process by which a planet's core and mantle separate from its crust. This is crucial for the development of a geologically active planet, as it influences tectonic activity, magnetic fields, and even the creation of a viable atmosphere. The end result is a planet that not only orbits its star, but also has the potential to support a variety of processes, including perhaps life. As protoplanets grow, they begin to differ drastically based on their location within the protoplanetary disk. Those that form farther from the star, where ice can remain solid, often grow into gas giants, like Jupiter and Saturn. These planets begin as icy cores that accumulate vast amounts of gas from the surrounding disk, growing to immense sizes. Closer to the star where ice cannot survive, rocky planets like Earth and Mars form. These planets start as silicate-rich planetesimals that accrue more material over time. The intense heat from the young star causes any volatile compounds to evaporate away, leaving behind dense rocky bodies. The composition and size of these planets are heavily influenced by the materials available in their particular region of the disk. The final stages of planetary formation involve the clearing of the surrounding disk, as the new planets use their gravity to sweep up remaining debris. This process can take millions of years, and it's marked by a decrease in collisions as the system stabilizes. The end result is a fully formed planetary system, each body locked in its orbit around the star, ready to undergo its own unique evolutionary history. Planet Earth is indeed a special case when it comes to planetary formation. Its position in the solar system provided the perfect conditions for life as we know it. Located in the habitable zone of the Sun, Earth was able to retain liquid water on its surface, a crucial ingredient for life. This positioning, combined with a favorable atmosphere and magnetic field, has protected life on Earth from solar radiation and cosmic impacts. The formation of Earth involved all the processes discussed, from the accretion of planetesimals to the violent collisions that shaped its core and surface. Each step in Earth's formation contributed to its ability to support life, from the differentiation that created its magnetic field to the volcanic activity that recycled carbon and stabilized its climate. Moreover, Earth's large moon, believed to have formed from a colossal impact with a Mars-sized body, has played a significant role in stabilizing the planet's climate and axial tilt. This stability is crucial for maintaining the seasons and climate conditions that have allowed life to thrive. Earth's story is a testament to the complexity and serendipity involved in planetary formation, a series of cosmic accidents that created a world teeming with life. The concept of the Goldilocks zone is critical in understanding planetary habitability. This zone refers to the region around a star where conditions are just right for liquid water to exist on a planet's surface, an essential criterion for life as we know it. Not too hot and not too cold, this zone is where planets are most likely to have environments that can support life. Earth's placement in the Sun's Goldilocks zone has been vital for the development and sustenance of life. However, this zone can vary widely around different stars, depending on the star's size and temperature. For instance, larger, hotter stars have Goldilocks zones that are farther out, while smaller, cooler stars have closer habitable zones. The study of exoplanets, planets outside our solar system, has expanded our understanding of the Goldilocks zone. Many exoplanets discovered in these zones raise the possibility of other life-bearing planets. These findings not only deepen our understanding of planetary formation, but also fuel our curiosity about life's potential ubiquity in the universe. The discovery of exoplanets has revolutionized our understanding of the universe and planetary formation. These planets, which orbit stars other than our own Sun, come in an astonishing variety of sizes, compositions, and orbits. The study of these distant worlds provides invaluable insights into the processes that govern planetary formation and the potential for life elsewhere in the universe. Exoplanets are often discovered through methods such as the transit technique, where a planet passes in front of its star, briefly dimming its light, or by the wobble in a star's position caused by a planet's gravitational pull. These techniques have revealed systems that are profoundly different from our own, with some stars hosting large numbers of gas giants or systems with tightly packed terrestrial planets. The diversity of these planetary systems has challenged our previous understanding of planetary formation and habitability. By comparing these systems to our own, scientists can refine the models of how planets form and assess the likelihood of other habitable worlds. This ongoing research not only satisfies human curiosity, but also has profound implications for our understanding of life's potential across the cosmos. The formation of planets is a complex and awe-inspiring process that spans millions of years and involves a series of intricate and interconnected stages. From the collapse of molecular clouds to the violent collisions of planetesimals and the final assembly of planetary cores, each step in this cosmic recipe is critical for the creation of the diverse planetary systems observed throughout the universe. Understanding these processes not only provides insight into our own origins but also into the potential for life elsewhere in the universe. As we continue to discover new planets and learn more about their formation, we expand our knowledge of the cosmos and our place within it. The study of planetary formation is more than an academic pursuit. It is a journey to understand the very processes that might lead to new worlds, new possibilities, and perhaps new beginnings. In conclusion, the birth of planets is a testament to the complexity and beauty of the universe. It reminds us that our existence is not an isolated phenomenon but part of a grander, more intricate cosmic ballet. By studying planetary formation, we not only unravel the mysteries of our past but also pave the way for future explorations into the vast unknown.